Hi, welcome to this course on Autonomous Cars 101. This course is meant for people that know how to use ROS and have interest in starting with autonomous cars. In this course, we're going to learn how to use the sensors available in any standard autonomous car, how to navigate using GPS, also generate algorithms for obstacle detection and security system implementation. And finally, we're going to use the CAN bus protocol, as all the cars use it in the industry. And at the end, we are going to do a micro project where you'll have as objective moving your car along the road to get to the gas station. Ready? So the first step is obviously going to Robotics Academy and log in to the web page. Then select the course that you want. In this case, we're going to select ROS Autonomous Vehicles 101. And you'll get something like this. You have a notebook where all the details and all the explanations are. You have an IDE where you generate your code, then 4 web shells and the simulation. So let's start with a simple exercise, which is moving the car. This is a very good exercise to get a feel of how a simulation works. In this case, how this car handles. So this command in particular, it's called unsafe test because it's not using all the security systems that are already online in this simulated car. In this simulated car, you have obstacle detection, and if we ought to use the standard topic where you send the moving commands, it would stop when it detected some obstacle. Also, it has a system that if you don't publish with a certain rate, it will stop the car. So for those 2 reasons, we are using this unsafe, just to move the car around. So you can turn, you can go backwards and turn backwards. You can stop, and you can increase or decrease the speed. So we can increase the speed and stop it. That's it. So play around with the car, and when you're ready, let's go to the next unit. Welcome back again. So this unit is about sensors. So you're going to learn how to use the laser, how to use the camera, and how to use the GPS. Let's have a look on how to see all this information. The best way to see this information is with RViz. But first, we have to know which topic has that information. So let's have a look. Let me see. There we have it. So in this case, we have the laser data in this CAT vehicle front laser points. Let's have a look. There we have it. It's the basic sensor messages laser scan message, nothing strange about it. And you will ask, okay, how can I see this laser data? Of course, you can do a ROS topic echo, which is useless in this case because you won't have the idea of what the car is really seeing. So let's execute RViz. Just type ROS run RVis, and wait a few seconds. There you have it. The first thing you have to do, as you might well know, is select the base, the fixed frame. In this case, we're going to select the cat vehicle autumn. Then let's add a robot model to have some sense of reference of where the car is. And then let's add the lasers. There we go. Then we select the topic and we should see something. I can't really see anything. Well, you may see some tiny dots there. Let's make them a bit bigger. Much better now. So as you can see, these are the 3 boxes that the car has just in front. And if we move, let's move as we did, cat vehicle test package, and then CMD unsafe. So if, for example, we turn, you can see here how this data changes in real time. Let's stop the car. And that's basically it about lasers. Let's go to the next set of sensors. Cameras. This is my favorite. The same thing. Where do we have camera data? It's very important just because then you have to select the topic with that data. Now let's have a look. Camera. You have all these topics with data about cameras. In this case, we are going to use this image raw front. It's the front camera that it's around in this tiny white box here. In the real car, you'll have it not here, but in the windshield, but more or less it is the same location. This one is a bit more, it's better in visualization, but actually you'll see more or less the same. So let's have a look. So you can use RVis to visualize, of course. How? Just you have to select here image and then select and blah blah blah. But we're going to do it in a different way. Let's close this. Let's save it for later. And let's execute this RQT image view. This is a dedicated program just for viewing images, which comes in handy. There we have it. So we select, this filters all the topics and just shows us the topics related to images. And we wait. There we go. So this is the images that are captured by the camera in front of the car. So if we move the car, for example, I don't know, let's move it around. You can, there we go. Now it's updating. Where's the car? Oh, here's the car. So as you can see, the update, it seems quite slow. We just lowered the frequency rate to make the simulation go much smoother. In reality, you'll have a higher frame rate, so don't worry about that. There we go. And finally, we're going to visualize the GPS data. The GPS data is published in two topics, in this fixed topic and this fixed velocity topic. It's also published in other topics, but we'll see it more in depth in Unit 4, I think. So let's have a look at this. In this case, we are going to use RViz, but we're going to use it in a special way. There are two ways of visualizing GPS data. One is generating markers to see waypoints or seeing the GPS data that it has in particular, but there's a very good way of doing it, which is with this RViz satellite plugin. So you have an example here of how to do it manually. We're going to use an already predefined file so that we go faster and you can see the results immediately. So we fire up RViz again. We check this path that we give you here, which is OPT ROS Indigo Share Cat Vehicle RViz config, and select the cat vehicle GPS. So here we can open this one. Let's have a look. OPT share and cat vehicle. You have two predefined. This one has all the visualization of the lasers, LiDAR also, and so on. And this one has... No, I don't want to. There we have it. So, what should you see here? So here, if we zoom out really far away, we have a tile, a map tile, that is fetched from this. Maybe we can see better here. Yeah, from this website. You can go to this website, sign in, and get your access token that you'll replace. Instead of the one that it's placed here, you'll place your own if you want to do it manually. But everything else, you have to leave it just as it is, because what it does is get the X, Y, and Z, let's say latitude, longitude, and altitude of the fixed topic, which you're selecting here, and it's putting that data, and it puts the car exactly in the place where the fixed data of the GPS is giving. This means that this car, based on its GPS sensor, that it's virtual in this case, it's based in Germany. It's based in Germany because we started the simulation with those initial values, but you can change those values obviously in any simulation that you generate. And then this makes, now we can move the car. Let's have a look. Okay. We're moving the car around, and it's moving in the map, and the laser data obviously is updating, and if we use the camera, we could see it also. So now you have a car that it's moving with GPS data in the real location where it should move. Isn't that amazing? The cool thing of this is that you could use these same tools for a real car that it has GPS topics published and laser topics. And I think that's quite it. So congratulations, you have more or less the idea of how to work with the sensors in this car and in any car that has ROS topics published. So if you don't have any doubts, let's continue. Unit 2 talks about the GPS navigation. It's quite straightforward because we want these courses to be very practical. We start with this exercise. This exercise is meant to get you used to using the GPS data. In this case, you have to do an action client that what it does is, given a waypoint, it returns the distance from that waypoint. That means that if you move, it should return as feedback the distance updated. And it updates because it's reading all the time the GPS data and it's comparing it with the waypoint you gave him. So this exercise is just to get you working on that matter. At the end of this exercise, you should have an algorithm of some kind that makes the car more or less go to the waypoint based on the distance. So if it detects that the distance is getting lower, then it has to change direction until it detects that the distance increases. It's very basic, but it's meant to that, what I said, that you get used to using GPS data. Let's have a look. So here you have the more detailed, the exercise. And then you have to bear in mind this, which is quite important. When you publish, you will publish in this topic. This topic is using let's say the node that it's reading this topic is using obstacle detection and a security system that we'll talk about a bit later, which is the dead man switch. This means that if you don't publish these, the message, the movement message, the twist messages with a certain rate, in this case 5 Hertz, the car will stop moving. Bear that in mind when you generate the algorithm to move your car, because maybe you think you just publish and the car will continue moving forever. And no, you have to publish it with a frequency of around 5 Hertz. So have a try with this exercise, pause the video, and when you finish, let's have a look on the solution of a possible solution, or more or less what it should give you. Yeah, so I have prepared a pair of scripts here, which are essentially the action client and the action server that we're going to launch. So let's close things that we don't need. This way we are not overexerting the system. And then ROS run, you will have to do that. I suppose you did more or less the same. Then GPS action server, and then we do the same thing. Autonomous car, GPS, action client. As you can see, I have a client that what returns is the distance. So now if I move the car, let's say ROS launch, ROS launch cat vehicle test, and I'm going to use the unsafe just to go faster. And I start to move around. Let's go back, see what happens. In this case, we finished. That's because I got the waypoint in the place. So, as you can see, it was giving a feedback of the distance. And when it got to the distance, more or less at a distance of around less than 3 meters, which is the distance, it stopped and gave me a result. That's essentially what you have to do, just that you have to do an algorithm that moves the car around based on that information. And that's all. So, did you manage? Was it difficult? Okay, so let's go to the next unit. This unit loads a different simulation. This simulation is the exact same car and world, just that this car doesn't have the obstacle detection and also the dead man switch system. This implies that it doesn't work. This car won't move. And what you're going to learn in this unit is how to do an obstacle detection and also how to implement the security system that has this dead man switch protocol. Also, you learn how you transform the twist commands into joint commands that move the car. And they will move the car using the Ackermann Steering model, which is widely used in any car nowadays. Ready? I'm going to explain more or less what the idea is. So, first, have a look at this diagram. This is the diagram of how more or less the information is transferred through our system until the car moves. The first step is the keyboard teleop in this case, or any command vel that it's published. Then this command vel is read by this obstacle stopper cat vehicle, which is the first barrier, the first security barrier. This node, what it does is read from this distance estimator, this topic that generates this distance estimator distance, which gives you the lower distance to any object. So for example, if you have no objects around except one just in front at 3 meters, it will give you 3 meters. Based on this information and the cat vehicle CMD vel that you are sending, it filters it. If the distance to the object is less than 3 meters or 5 meters or whatever you stated inside, it transforms this command velocity message into a 0 command velocity, so the car doesn't move. If there is no object nearby, then it just copies the message that you sent. Then the next step and final step is this command vel to gazebo, so on. This one, what it does is reads from this command vel safe, which it's safe because now there's no obstacles. And what it does is record at what frequency it's receiving this messages. If this frequency is not high enough, then the deadman switch comes into place. There are many protocols of this deadman switch, but in this case, it's implemented that it will stop the car until it gets the next message. And what it does this is it gets this command vel safe and sends the commands to the joints and moves the car based on this command vel using the Ackermann steering model. Yeah. So the exercise. Create a publisher that sends commands to the joints of the car and wheels. And we give you some information about it. So you have to publish here. Where you have to publish to move the car is around here. So front left steering position controller. So this is for steering the wheels. And this is for moving the wheels. So make the wheels turn, the ones from the back. Yeah. So in this case, it's only velocity controller. And here we say that you can move the car as you wish. You don't have to use the Ackermann steering model, but it's highly advisable that you learn how to use it, because in all the simulations and in all the car systems, the real systems, there is some version of the Ackermann steering model implemented. If you don't know how this Ackermann steering works, have a look at this video. It's really nice. You'll have a very good idea of how this is implemented, the basics at least. So have a try. Pause the video, and when you come back, I'll explain more or less the code that you should use and the details around it. Okay, welcome back. So the first thing is generating this command vel to gazebo, which what it does is reads from the command vel safe and publishes into the controllers that move the wheels. It has some data, for example, the dimensions of the car, and you say, why do I need the dimensions of a car? Because Ackermann steering model is based on how wide the car is and what's the distance between the front wheels and the rear wheels. It also makes some calculations and so on, and starts the timer. This is very important for the deadman switch implementation. Then we have this publish method, which evaluates first if the message, where is it? The CAD vehicle command vel safe, when was the last one sent? And this is how you implement the deadman switch. If it's too old, then we don't move. It's just you're generating this float 64. So here, when the message is too old, you just generate a message that sends a command that makes the car stop. That's it. Then you have two cases. One is when you're steering, and the other one is when you're not. This is the angular velocity Z. This angular velocity is the angle in radians, is just how much you want to turn the wheels. So you make some calculations, and here is where the Ackermann steering model comes into place. Essentially what it does is the inner wheel, let's have a look to the simulation. So if we are going to turn, let's say to the right, this inner wheel has to turn a bit more than the outer wheel. In this way, it turns better. Is essentially that. Also, the rear wheel might have to go a bit faster than the other one, or the other way around. Depends on how you turn. So this is what you're doing in this code. As you can see here, the turning, and then to the rear, you see there's a slight difference. Yeah, to the rear, the left and the right. You see, these ones are the rears, so they will go a bit faster depending on in which direction you're turning, and this one also. This is the steering, how much you steer the wheels. In the case that it doesn't move, it's going straight forward, it's really easy because they do exactly the same and they move exactly the same. Yeah? And that essentially is the idea around here. Then the next step is the obstacle stopper. So this one, what it does is detect an obstacle. In this exercise, you just have to read from this distance estimator. You're not reading from the lasers directly. You're reading from a node that it's pre-made and gives you the closest object and at what distance. So the same thing. Try it and then come back and see more or less my explanation on some details. Welcome back again. As you can see, it's a very, very simple algorithm. There's nothing more to it. Just you publish in the command vel safe and you read from this one. You read also from the distance estimator, and it's based in this callback. This means that when you get messages from this one is when you publish here. So you'll publish more or less at the same rate in both topics. And essentially what you're trying is you see if the distance is lower than a value, and that's it. If it's lower, then it's 0, the linear. If it's not, then it's not. That's it. And that's it. Congratulations! Now you know how to visualize the sensors, how to navigate with GPS, and how to implement some very simple obstacle detection and security systems. If you're ready, let's continue. So this is Unit 4, and we are talking about the CAN bus. The CAN bus is a protocol that was created by Bosch, the company Bosch, and it was around late 70s, and it's a protocol that was generated to multiplex signals in a few electrical wires. This was created for the necessity and for many other reasons, but one reason was because they started to put electronics in the cars, and they saw that they needed so many cables, and the cable management was becoming a monster. So they generated this protocol that makes transfer information through 2-3 wires. Very few wires are needed to transfer a lot of information. It also has other features like security features and so on to validate that the messages sent are correct and they're not corrupted and so on, for security reasons basically. So if you know how the CAN bus works, just jump to the exercise, the first exercise, U4.1. If you don't, stay a bit longer. So essentially the CAN bus messages have three parts: the identifier, the data length code, and the data that you have colored here in green, yellow, and red. And the topics that we're going to use that have this CAN codification have the exact same variables. So you'll have a variable that has the identifier, you'll have a variable that says how long, the DLC code, and then you'll have the data. All of them will be coded in integers and so on. So in data, let's say in bits of data, as it would be in the CAN, the real CAN. So you learn that now using the CAN bus, you will publish in some topics that are real, let's say steering, throttle, pedal, brake pedal, and gear selection, and this will be transformed into CAN information and transmitted through the CAN bus to the car systems. And the car will return data in CAN protocol also, and you'll have to transform that information to information that you can understand and publish in a topic. But that's the real way of doing things. It's not through topics. The vast majority of information, it will be transmitted through CAN bus. So let's have a look on how this system works. And for this, you have to execute the RQT graph. You'll get something like this. As you can see, this is quite complex, and I think we have to talk about this. So this region around here, it's the simulation, or it would be the car. And this region would be the bus driver device. We have made it easier to understand with these diagrams. So what you have in reality is this: you have a car and you have this device, and this device would communicate through USB with a node, in this case this CAN bus DBW, that will then convert that information, that bus CAN information, to topics. There you have it. But that information, it's in CAN bus standard, so it will just transform it to topics, but it's still encoded. This node, the vehicle DBW node, will be the one in charge of transforming this, of reading this data. This is the output and this is the input. So it will publish here and it will read from here. In the simulation, you have the exact same thing. The only difference is that the device, the real device, it doesn't exist, and it's simulated also. So we have simulated that part also. But essentially it's the same. You'll just publish some topics that this vehicle DBW will read, and then it will code it to CAN bus protocol, and from there it would be exactly the same thing. Why have I explained all this? Here you have the RQT graph. It's exactly to see exactly what I showed you. You have to select all the nodes to see everything, all the topics, all the nodes, everything. Why did I explain this to you? Because I want you to be aware that all the things that you do from now on have to be having in mind that there is no topics. There is no twist message that you publish and the car moves. You will have to publish into topics that, like steering, or like how much I pressed the pedal, because that's real information. And that information then will be transmitted through bus scan to the different devices in the car that will interpret that data and will press the throttle or move the wheels and so on. Yeah? So this exercise is meant to make you aware of that, make you aware that you have to publish in these topics. For example, vehicle brake command. You see, now it has this namespace, vehicle. This means that this would be a topic that the vehicle would have, the real one would have. So you have to publish here, and this will be transformed into information for the CAN bus. Yeah? I have some explanations around here on how to publish, how to get these commands published, because you can't publish them and that's it. This node that transforms this information to buscan or CAN bus needs this message being published before, which is vehicle enable. So you have to send a message through this topic to enable the publishing of this. This is a security measure so that you don't publish steering or throttle messages by accident. And then there are some special things that you have to bear in mind when you publish this kind of information. For example, in the bus scan protocol, the brake command needs to know which type of pedal is it, which type of data you're sending, because you can send how much force you're exerting over the pedal, the percentage of how much you're pressing the pedal, or just a number. So in this case, and in the throttle case, use this pedal command type 1, which makes you send any number, and it's much easier. But you can dig in and see in the messages which type. Here, if you look for the brake command messages, you'll have a good idea of how it works. Now let's have a look. For example, ROS message show db messages and brake commands. There we go. So do it a bit bigger. So in this case, you see that for publishing this type of messages, you need some variables here, but also you have some commands. And it depends on how, for example, in the pedal type, you can select if you want torque, if you want to send in the pedal command, it's torque, it's force, or percentage, or just pedal information, or none, if you don't want to move the pedal. Yeah? This is one thing. Then also the gear messages, it's quite arbitrary because it's numbers. It's not something that you could understand, or you could imagine that it's 1, 2, 3, 4, 5 for gears. So the same thing here. You go here and you select gear command, and as you can see here, the gear command, the gear, you can select 0, 1, which is park, reverse, neutral, low, and so on. And that's quite it. Have a try. It's to publish. In theory, it's just publishing into topics, which wouldn't be that difficult, but these tiny details like this, for example, you have to be sure that it's enabled, otherwise you'll start publishing and it won't publish anything because you didn't enable it and you didn't wait for the enable to get that data. So you have to do some try-catch system that makes it to make sure that you publish that data. Understood? So pause the video and we'll come back when you finish, or when you need some extra information. Welcome back. Here you have an example of this car control. So how do you move it? How do you publish this? In this case, we did a class with publishing this, then the enable, then it makes a loop, which tries and tries and tries until it works. Yeah. When you have it enabled, just wait for the physics to be up and running. This is not necessary because you have it already running, but for simulations, it's a good thing to have. And then we publish. So we have different methods to publish different things. So you have it all this here, but for example, the throttle command. The throttle command, it's getting this throttle command from this package, dbwmkz messages. And let's see. For example, here you put the throttle value, the pedal type, which is 1, and the rest you can put it by default. So false, false, and 0. And that's it. You do the same thing more or less with the brakes, and more or less the steering has a bit, but more or less is exactly the same. You say the angle and the velocity in which you're moving. You want to move the steering wheel, and the gear is just selecting the gear. So if you want to go forward, then let's see, go forward, drive, number 4. If you want to go reverse, 2. That's quite it. Yeah. So if all went well, you should have something similar to this. So you have a testing system to do this, which is here we go. This is an example of how it should more or less work, your system. As you can see, it stopped moving because it's detecting an obstacle. If I remove the obstacle, it will start to move again. Okay, this is just an example of how it should work. As you might have seen, at first it made some tries because it tried to send the enable, but as you may know, the topics not always work the first time, so you have to try and try some until it works, and until the channel is open, and then a few more tries to be sure. And when you have, essentially what we're doing here is reading the topic. So if the topic receives that message, then it's good to go. Yeah. Okay, congratulations. This is the main exercise. If you want to do an extra exercise to know more about the CAN protocol and so on, keep on reading. So this, you need C++ knowledge, because we will be going over some C++ code, and to generate your own code in Python or in C++, you'll need to know how to do this. Yeah. This exercise has the objective to show the basics of CAN bus. The first things you'll have to do is subscribe to the CAN bus topics. This is the output and this is the input, let's say. Then essentially what you're going to do is read and know what kind of data is running there. So we're going to decode the encoded data. And that's what the exercise is all about, is making a decoder of both channels so that you have a control of what is being sent. And you'll see the brake commands, you'll see the throttle commands, you'll see also in the RX, which is the input, the GPS data, and you'll see that it has different morphology. So just a few tips. These are the IDs, and as you can see, you have to transform them from X format to decimal format first to know what type of messages are sent. This is one of the first steps I would recommend. Then when you have more idea, then you have to dig in how the data is encoded and how it transforms the twist messages or the steering, the throttle messages into this integer coding messages. Because if we have a look, for example, I don't know, let's have a look. So if we start and we do ROS topic echo -1 this. Yeah, for example, this is an example of how the data is encoded in this topic. As you can see, it makes no sense, absolutely no sense. It has a data which is 255, and an ID and DLC. So the first exercise is know what this stands for. Is it the throttle? Is it the brake? Is it the gear? What is it? And then the next step is decoding this data to know what is it. Yeah. So you'll have to have a look to this db can. So let's have a look, and I'll leave you there. db can. Yeah. So you have this extra docs that we copied here, and this is the code of the node that it's already running, and you can have a look inside and see, okay, so I'll have a look, for example, this dispatch H, and you see that about that. Yeah, there we go. You have here the defined structures of these messages. For example, this message break command has this PCMD, which is the data, more or less the data, and you see that it's 16 bits of information. You may see, if you know about CAN protocol, is that all the messages sent in this version of CAN are 64-bit and nothing else. So all the messages have to have these 64 bits. Yeah. Okay, so good luck with this. This part is tough, but I'm sure you can do it. Further references, you have information about CAN bus, books, the original protocol from Bosch, and the CAN bus hardware used in this car in particular. So you can have all the information available. Yeah. Okay. And that's quite it. The final unit talks about the micro project, which essentially is using the data from the bus scan. You see that this is vehicle GPS fix. It's not fix, it's vehicle GPS. So this is the data, the GPS data that went through the CAN bus and was decoded and published. And this is the topic that you would have in real life. Then you have some information, some topics that you would have, because it's the image and the lasers, which would go in their own channel maybe. And then, in this case on this car, go like that. And then you have how to control, how to move the car, and that's it. So with these 3 rules, you have to move the car throughout the environment. So here we have the environment. Let's make it a bit bigger. And you have the environment, and you have to move the car from here to the gas station around here. Yeah? So good luck with it. Use the laser, the obstacle detection, use the GPS, anything you want. Cameras, you can recognize, for example, the line and try to follow the line. Anything. Be creative. And now, now it's finished. What to do now? Well, what you can do now is, if you want to develop simulations and go further in the simulation development, or use the same simulations that you used here for free, go to ROS Development Studio, and there you can use them as much as you want and practice and generate your own simulations. If you want to learn more, then go to Robotic Night Academy to learn more about ROS navigation. We have RTAB, for example, we have OpenAI, we have topics about TF, and each month we have new topics. So you're more than welcome there. Then certifying ROS also, you can do online exams. And in behalf of all the Construct team and I, myself, Miguel Ángel Rodríguez, we thank you and hope to see you soon.